So this is two-sample hypothesis testing, and this is an example from your notes, example 5. So we need to see what we know, and then how we can use what we know. So reading through the problem, it says track tests at 5 miles per hour were performed on 5 randomly selected small pickups and 8 randomly selected small utility vehicles. For the small pickups, the mean bumper repair cost was $1,520 and the standard deviation was $403. For the small utility vehicles, the mean bumper repair cost was $937 and the standard deviation was $382. So at a significance level of 10%, test the claim that the mean bumper repair cost is greater for small pickups than for small utility vehicles, and assume that the population variances are not equal. So that means when we get to the question about pool, we are not going to pool. And we also notice that the significance level is 10%, so that means that alpha is equal to 0.1. So for the sample information, we have 2 sets. We have 5 randomly selected small pickups, and for the small pickups, the mean bumper repair cost was $1,520 and the standard deviation was 403. So we're going to take them to be group 1. So that means X bar 1 is 1,520. And that standard deviation 1 is 403. And the number in the sample was 5. And then it also says that we're testing 8 randomly selected small utility vehicles. So they're going to be group 2. And immediately, one of the things that you need to understand is as soon as you know your 2 sample sizes are different, you know that's going to be an independent sample. You know that for sure because N1 does not equal N2. Now, if they were equal, that doesn't mean that it's automatically dependent either. But if they are not equal, you know that they for sure are independent. So for the small utility vehicles, the mean repair cost was $937 with a standard deviation of 382. So based on what we have and what we've been told, we need to make some choices now. This is an independent test. We've been told sample standard deviations, not population standard deviations. So for that reason, the fact that it's independent tells us it's not a single t-test, it's a 2-sample test. And it's a 2-sample t-test because we're using sample standard deviations. So it's because we're using S, not sigma. So we filled in the chart. And step 3 says set up the hypothesis. So now it's time to look at the claim. Test the claim that the mean bumper repair cost is greater for the small pickups, that's group 1, than for the small utility vehicles, that's group 2. So what the claim says is that the mean for group 1 is greater than the mean for group 2. And what that also means then is if you were to take the mean of group 1 and subtract the mean of group 2, that difference would be positive, because if this number is bigger than this number, then you're going to get a positive answer. And that's going to make a difference in how we're going to set up the test. So since this is the claim, we need HO, and HO always says there is no difference. And that H1 says that there is a difference, and it says that this is the way the difference goes. That the mean of group 1 is greater than the mean for group 2. So then we're going to set up the calculator and work the problem and see how it comes out. Turn the calculator on. We hit the stat button, we go to the test menu, and we go to the 2-sample t-test because that was the choice that we made. And our input is from statistics, not data. And the mean for group 1 is 1520. And standard deviation for group 1 is 403. And the sample size for group 1 is 5. The mean for group 2 is 937. Standard deviation for group 2 is 382. Sample size is 8. And H1 is our claim. And the sign in the claim says the mean of group 1 is greater than the mean for group 2. And we're told not to pool the variances because they're not equal. So then we'll draw the picture and find out the test statistic and the p-value and see what we come up with. So in the middle of the curve, remember that's where mu1 is equal to mu2. And this would be where mu1 is greater than mu2. So this is the area that alpha is going to be in. And then the information we have from the test, scoot this out of the way for a second. Information we have for the test says that our test statistic, which is a t-value, is 2.5886. So that's that area right there. And that little bitty bit of shading that you're seeing up there is your p-value. And your p-value is 0.0157. 0.0157. And we always compare that to the alpha value, which is 0.1 or 0.10. And if alpha is 0.10, then that means it's bigger than the p-value. And that tells you then that your p-value is less than your alpha value. So that tells us how we can write our conclusion. And our conclusion is, because p is less than alpha, we will reject HO. And remember what HO says. Teacher can't spell. Is that there's no difference. So we are going to reject HO, which means we are saying that's not true. And if that's not true, then H1 must be true. So then what is actually true is the claim, because H1 is the claim. So we've made our decision. And all we have to do is go back and write a sentence that explains what the decision was. So our decision says that we rejected HO, we supported the claim, Now your sentence doesn't have to look exactly like that, but basically what we say is at the 0.01 level of significance, the evidence from the sample shows that the claim is supported and the mean repair for the small pickups is higher. Or you can say is higher than for the small utility vehicles. Okay? So the evidence supports the claim. this making sense to everybody? Okay. We have one more example. And this one says, listed below are body mass indices, which are called BMIs. They're related to weight, but more than just weight. They're related to density. So these are the body mass indices of students, and the measurements are taken in September and then again in April of the freshman year. Does the BMI appear to increase during the freshman year? Use a .05 significance level. Now, the first thing we have to decide is, are these independent or are they dependent samples?
Dependent.
How do you know, Matthew?
Because it's the same person's BMI. Like if their September BMI.
Right. So basically, the September BMI and the April BMI of 20.68, 20.15 came from just one person. Two different values from one person. That means your samples are dependent. And because your samples are dependent, we will do a single sample t-test, and the single sample is going to be the differences in those BMIs. So what we're going to do is we're going to use the calculator, and I think I showed you last time there's two different ways that you can actually do this. Since we have a relatively short list, we'll go with the way of just actually subtracting each one. Now remember, the way that you subtract these is always after minus before. Okay? So it's going to be April minus September. Because if there's going to be an increase, then the after has to be higher than the before. And that means then that this difference here is going to be greater than 0. It's going to be positive.
Do you only do after or minus before if the claim's talking about an increase, or you always do?
You always do after minus before, because that's where the change takes place. The change is, if it's going down, you'll just have a negative after minus before. And if you say there's no difference, well then after equals before. So when we do these, we're going to do 20.15 minus 20.68. So the actual first difference is negative 0.53. And then the second one is going to be 19.24 minus 19.48, which is also negative. And 20.77 minus 19.59. And 23.85 minus 24.57. And 21.32 minus 20.96. So looking at those differences might be a wash, because we've got 3 negative ones that are relatively small, and we've got 2 positive ones. One's kind of small and the other one's kind of bigger. So we'll have to see how this comes out. So we go to stat, we go over to tests, and we're going to choose the t-test because we're testing that column of differences. And we're actually working from the data that's in list 1. So now we need to set up our claim and our hypotheses. So we're gonna go back up here to the claim, and it doesn't spell out this is a claim, but it says, does BMI appear to increase during the freshman year? So that claim is that the difference should be positive. So it should be greater than 0. And if that's our claim, then obviously that's not HO. HO is there is no difference. In other words, the average difference was 0. So H1 says, yes, there is a difference, and the difference is positive. Because it did increase. So mu sub 0 is going to be 0. Our data's in list 1, and it's not a frequency distribution, so the frequency stays 1. And we're banking on our mean being greater than 0. So we will draw I see an awful lot of black, which indicates HO is the truth. So here's the result of our test. That line is where the average difference is 0. This says that the actual t-value is 0.029. And then our p-value is almost 50%. So when it comes time to compare P to alpha, P is definitely a lot bigger than alpha. It says that alpha is 0.05. P-value is not less than alpha, it is substantially greater than alpha. And we do not reject HO. The evidence doesn't support the claim. Because the claim is H1. So when we write our conclusion, and say the sample evidence does not support a claim that the BMI increases during freshman year. Okay? Anybody have any questions? Okay, in order for us to know for sure that you're doing okay on these, I want you to remember that we have a Chapter 9 assignment, and that's this review worksheet. It reviews both Chapter 8 and Chapter 9.
I had a question about problem 5.
Okay?
So is the claim would be that the mean of the difference is greater than 0, right? Because it's saying that it improves test
Improved scores, so yes, they're, after minus before would be positive. It would be greater than 0.
And the answers it's switched, but I guess that's just a mistake.
Okay, let me check, because I didn't necessarily write the answer, so let me double check and make sure what the answer said. Okay, it's because of the way that they did the subtraction, and that's why I always tell you to do it a certain way, because what they've done is they're doing before minus after rather than the other way around.
Oh, okay.
That would be my guess. But your conclusion would be the same.
Okay.
No, I mean, actually, the way you word your conclusion would be the same. There really isn't a right or a wrong way to do the before minus after. It's just that I tell you to do it that way we'll always be consistent in the way that we answer the questions in class. But then your conclusion should be the same either way.
Thank you.
Okay, well, that's all the examples. And we have time for a short break. And then when we come back, we're going to work on Chapter 10. So if you haven't printed off your Millions worksheet, please go ahead and do that. And we will start back up again in about 10 minutes.